In this talk, I will show you an example of how machine learning techniques can be used to solve difficult search problems, discover new algorithms, or new mathematical results. My name is Matej Balog. I work as a research scientist at DeepMind, where I am working on using machine learning techniques to discover new results in mathematics and computer science. And I'll be presenting this work on behalf of the whole AlphaTensor team. Just to set the context of this work, the high-level mission of DeepMind is to solve intelligence, to advance science and benefit humanity. And in the science team within DeepMind, where I also work, we are focused on the second half here. So we want to advance science and benefit humanity by tackling root node problems in different sciences, such as, for example, protein folding in biology and others in chemistry, mathematics, and now computer science. In this specific project, our goal has been to discover new, provably correct and efficient algorithms for impactful problems using machine learning. And here I would like to highlight the provably correct bit, that in this case we are looking for algorithms that are really exact and correct on every instance. We are not looking for approximations, neural or otherwise. Now, of course, discovering new algorithms is a difficult problem, even for humans, often requiring a lot of ingenuity. But we believe that by using machine learning, we can potentially reach beyond this realm of human intuition and also discover algorithms that can be more efficient. In this project, we focused in particular on the problem of matrix multiplication for two main reasons. One, as you know, matrix multiplication is a root node computational problem in the sense that it is used as a subroutine in many important computational tasks. This includes the training and evaluation of neural networks. The second reason is that, as we will see, for matrix multiplication, we can elegantly formalize the space of possible algorithms. So to see how we can do this, let's first recall what matrix multiplication algorithms even look like. So on the left, I am showing the simple case of multiplying two 2x2 matrices, A and B, together to obtain a matrix C. And in the middle, I am showing the standard algorithm for computing this matrix product, which uses 8 scalar multiplications, H1 up to H8. And there are 8 scalar multiplications because the output matrix C has 4 entries. And to compute each entry, we need to compute an inner product between two length 2 vectors, resulting in 4 times 2, 8 scalar multiplications. In 1969, it was quite a big surprise to the mathematical community when the German mathematician Volker Strassen presented this algorithm on the right-hand side, which only uses 7 scalar multiplications instead of 8. And what Strassen found is a way of cleverly adding up the entries of the two input matrices before multiplying them together in such a way that there are these 7 products, H1 up to H7, that are sufficient to build up the correct results in all the 4 output entries in the product matrix. So to verify that this algorithm on the right-hand side is correct, all one needs to do is to multiply out the brackets and check that the correct cancellations occur when you add up the terms as shown on the bottom right. But importantly, algorithms like Strassen's, they don't just apply to multiplying 2x2 matrices. If you have arbitrarily large n by n matrices that you want to multiply together, you can reinterpret these matrices as 2x2 matrices, where the entries are now block matrices themselves instead of being scalars. And you can apply Strassen's algorithm recursively. And when you do this, this saving of 1 multiplication, having 7 instead of 8, is really crucial because this means you save 1 matrix multiplication or 1 recursive call in the algorithm. And by doing the analysis, one can show that this recursive application of Strassen's algorithm results in an algorithm for multiplying n by n matrices whose time complexity is O(n) to the power of log base 2 of 7. So the exponent on the n is 2.81. Meaning this is a subcubic algorithm, something that people before Strassen didn't think was even possible. So Strassen's discovery has, of course, spurred this whole research area trying to discover faster and faster algorithms. And indeed, since 1969, people have come up with faster and faster algorithms. So on the vertical axis, I am showing the time complexity, the exponent of the time complexity, starting with Strassen at 2.81. And then over time, people have developed faster and faster algorithms. And the record of 2.37 is held by work just from last year. But as people construct these faster and faster algorithms, they rely on more and more sophisticated constructions, let's say from group theory or other more advanced branches of mathematics. And as a result, the algorithms that are the fastest in theory or even come close to being the fastest, they would only be fast in practice on matrices that are much larger than what we would ever construct in this universe. So I don't believe that the algorithms that are actually theoretically fastest have ever been implemented, or certainly they haven't been used in practice. Yeah, I'll get to that. So the horizontal axis is basically the smallest matrix that you can apply this algorithm to. That can be a...
That's n or n squared.
Sorry, say again?
That's n for n by n matrix.
Yeah, that's just n. So for Strassen, we have 2. That's for 2 by 2 matrices. And then for the larger ones, it's really just an estimate based on the construction. But it's just to illustrate that the matrix would need to be really, really huge for this to be applicable. So on the practical end of the spectrum, so when we want to look at the cases that we can actually implement in practice, for 2 by 2 matrices, it is known that Strassen's algorithm is optimal. So it's not possible to multiply 2 by 2 matrices using 6 multiplications. But already for 3 by 3, the space of possible algorithms is so huge that we only know that the optimal number of multiplications is somewhere between 19 and 23. Which is quite unbelievable because 3 by 3 sounds so small. So we have this question still wide open. Are there algorithms in this orange region which are both practical and fast? So now to see how we might even start to answer this question about an existence of an algorithm, recall that I mentioned one of the reasons we look at matrix multiplication is that we can elegantly formalize the space of possible algorithms. So let me try to explain this. On the left, I'm again showing this operation of 2 by 2 matrix multiplication. And this operation is bilinear, meaning that it is linear in both arguments, a and b. And just like linear operations can generally be represented using a fixed 2D matrix, bilinear operations, like matrix multiplication, can be represented using a fixed 3-dimensional tensor. For this particular operation, the 3-dimensional tensor is of size 4 by 4 by 4, because there are 4 elements in both input matrices, and there are 4 elements in the output matrix. The tensor representing this operation I'm showing on the slide, it's a fixed tensor, independent of the contents of the matrices that are being multiplied. The tensor only contains zeros and ones, shown in gray and blue, respectively. And what this tensor intuitively encodes, it says which of the entries of the input matrices should be multiplied together, and into which entry of the output matrix the product should be written to. So as a specific example, let's look at the output entry C22, the lower right entry of the output matrix. As we know, this needs to be the inner product of the second row of A and the second column of B. And if we look at the slice of the tensor corresponding to C22, which is the slice facing to your right, we will see that we have an entry of 1 in the position corresponding to A21, B12, C22. And we have another entry set to 1 corresponding to the other product in the inner product. So this tensor, it only describes the operation of multiplying the 2 matrices. It says what the output should equal to. It doesn't say how we should algorithmically compute it. So if we have a specific algorithm for computing the matrix product, such as Strassen's algorithm, I'm just showing it again on the slide, it turns out that in this tensor language, this algorithm corresponds to a low-rank decomposition of the matrix multiplication tensor into a sum of rank 1 tensors. This concept of decomposing into a sum of rank 1 tensors is the same as we know for matrices, but in this case, because the tensor is 3-dimensional instead of 2D, each rank 1 term is an outer product of 3 vectors instead of 2. In this decomposition, we have 1 term for every scalar multiplication appearing in the algorithm, and the 3 vectors that form one of the terms, they describe or encode which entries of the first input matrix to take in purple, which entries of the second input matrix to take in green, and then once you have the product, H1, into which entries of the output matrix, C, to add this product to. So in this particular case, the first product is A11 plus A22, times B11 plus B22, and we encode this using one-hot encodings in those vectors. And then we have one term like this for every scalar multiplication in the algorithm, as I just said. And so in this tensor language, to verify that we have a correct algorithm, to verify that Strassen's algorithm is correct, all we need to check is that this decomposition, when you add up the terms, actually adds up to the matrix multiplication tensor. And so in this language, Strassen's discovery from 1969 basically says that the rank of the matrix multiplication tensor for 2x2 matrix multiplication is 7 instead of 8. So to summarize this view in different words, to discover new algorithms for multiplying matrices, we can phrase the problem as follows. We are just given this one fixed tensor T, the matrix multiplication tensor, and the task is to decompose it into a sum of rank 1 tensors. And the fewer terms we manage to do it with, the smaller the capital R will be, the fewer scalar multiplications there will be in the corresponding algorithm, and the faster it will be. So now comes the main underlying idea of this work, and it's that we took this tensor decomposition problem and we turned it into a single-player game. In this game, the state of the game, or the game board, is described by a three-dimensional tensor. And at the beginning of the game, we set this tensor to be the matrix multiplication tensor. And then in each step of the game, the player needs to choose these three vectors, u, v, and w, that implicitly, through their outer product, describe a rank 1 tensor. And once this move is chosen, the state of the game is updated by subtracting this rank 1 tensor from the previous state. So on the slide, I'm showing the changed entries in green. And this process is repeated, the player writing down three vectors and then subtracting the rank 1 tensor, until the player manages to reach the 0 tensor. So all the entries are zeroed out. And when this happens, the factors that have been written down throughout the game, all these vectors u, v, w, they must form a valid decomposition of the matrix multiplication tensor, because that's the tensor we started with, and at the end we reach the 0 tensor. And so to encourage the player to find the shortest path from the matrix multiplication tensor to the 0 tensor, we give a reward of -1 for every step taken in this game. So far, I have illustrated how discovering algorithms for matrix multiplication can be...
So then the game is to reach 0 as fast as possible.
Yeah, that's right. So far I've used 2x2 matrix multiplication to illustrate how discovering algorithms corresponds to tensor decomposition and how tensor decomposition can be phrased as a single-player game. But as I said, for 2x2 matrix multiplication, the problem is solved. It's known that 7 multiplications is the optimal. It's for larger sizes that the problem is open. But everything works in exactly the same way, except that this matrix multiplication tensor will be bigger. So in this fancy illustration, I'm showing a tensor of size 16 by 16 by 16, which is the size that represents 4 by 4 matrix multiplication. And as you can see, it can be quite a complex object, at least for me as a human. But the good news is that once we train a reinforcement learning agent, AlphaTensor, it is able to somehow detect patterns and understand this tensor and discover valid factorization, so reach the 0 state, corresponding to very, I would say, complex algorithms, like the one shown on this slide. It's not legible, but just to illustrate the complexity of the algorithms that we can discover, or we need to discover. More specifically, we applied AlphaTensor to discovering matrix multiplication algorithms for different base matrix sizes, including rectangular matrix multiplication. So this is the problem of multiplying an m by n matrix with an n by p matrix. And I call these base matrix sizes because, as I explained with Strassen's algorithm, all these algorithms can also be applied to larger matrices through recursion. So in this table, I'm now showing the prior best known ranks, or the smallest known number of multiplications required to multiply matrices of these specific sizes. On the left, starting with Strassen, that's 2x2 with 2x2. And we train AlphaTensor from scratch without any knowledge of these existing algorithms. And what's nice is that as AlphaTensor keeps training, it gradually rediscovers these previously known algorithms, starting with Strassen for 2 by 2, then Laderman's algorithm for 3 by 3, and larger sizes follow. And what's exciting is that as AlphaTensor continues to improve, for some of the larger sizes, it is able to discover algorithms that use strictly fewer multiplications than what had previously been known. And in fact, AlphaTensor discovers not just one algorithm for each matrix size. For most of them, it discovers thousands of non-equivalent algorithms, which is interesting in itself, and I will comment on that later. Now, just like Strassen's algorithm, all these algorithms discovered by AlphaTensor, they use integer coefficients. And this has two implications. One is that these algorithms are really exact. There are no round-off errors from having real valued coefficients in them. And two, these algorithms can be used to multiply matrices over any ring. So in particular, all these algorithms we can use to multiply real matrices, the most common use case. However, AlphaTensor is quite flexible, and we can also use it to discover more specialized algorithms for specific rings. So for example, if you want to multiply matrices over finite fields, let's say F2, arithmetic modulo 2, then it's quite easy to adapt AlphaTensor to this setting. And in this case, it is able to discover even faster algorithms also for 4 by 4 matrix multiplication using 47 instead of 49 multiplications, and for 5 by 5 matrix multiplication. The first result was particularly exciting for us because this has been the first time that there was an improvement over Strassen's algorithm for 4 by 4 matrix multiplication in any field since Strassen's algorithm was invented more than 50 years ago.
Excuse me, how do you initialize your agent? Does it have an influence on the...
So we don't give it access to existing algorithms. The neural network is initialized purely randomly in the agent. But as I will talk about a bit later, we do provide it some bias through synthetic demonstrations. But those have nothing to do with the problem of matrix multiplication. It's just some demonstrations on how to decompose random tensors. Yeah, but I will explain that later. So as I alluded to before, AlphaTensor discovers not only one, but in fact thousands of non-equivalent algorithms for almost all matrix sizes. And this has multiple implications. One, this is already interesting from a mathematical point of view, because these matrix multiplication algorithms and their symmetries are fundamental objects in algebraic complexity theory. So it is of interest to this field that this space of algorithms is much richer than previously thought. And in particular, I would like to highlight this one result, that before this work, the only known way to multiply 4 by 4 matrices using 49 multiplications was to apply Strassen's algorithm recursively twice, resulting in 7 times 7, 49 multiplications. But AlphaTensor discovered more than 14,000 provably non-equivalent algorithms, all different from Strassen and also having differing mathematical properties among themselves. One way in which we ourselves exploited this diversity of algorithms that AlphaTensor can discover is that we explored the different ways in which algorithms for small base matrix sizes can be combined together to obtain algorithms for slightly bigger base matrix sizes, let's say multiplying 9 by 9 matrices. And by exploring all these possible combinations, we have been able to improve the best known rank or the smallest number of multiplications needed for more than 70 different targets up to 12 by 12 matrix multiplication. So on this slide, I'm horizontally showing the previously known best rank, and vertically I'm showing the improvement. And as you might expect, the bigger the rank was previously known, the more we were able to improve it. And finally, we have used this ability of AlphaTensor to discover not just one, but many algorithms with the same rank or same theoretical time complexity to encourage the agent to narrow down its search towards those algorithms that are actually fastest in practice if we implement them and run them on a specific, let's say, hardware accelerator, so maybe a GPU. And this was actually very easy to do in the AlphaTensor framework. All we did was we added an additional term to the reward of the agent, which was the negative of the runtime when we benchmarked the algorithm on, let's say, the GPU. And with this additional term in the reward, AlphaTensor has been able to discover algorithms that multiply matrices between 10 to 20% faster than the usual baseline, assuming that the matrices are large enough. So in this case, larger than around 8,000 by 8,000. So now, having talked about the main results, I would like to talk a bit about the method itself. So AlphaTensor is based on AlphaZero, which is a reinforcement learning agent that was originally developed for human games like chess, Go, and shogi. And the way an AlphaZero agent plays a game is visualized here. So in each state of the game, the agent uses a neural network to build this tree of possible futures. And then based on this tree, a Monte Carlo tree search, it picks one action to actually commit in the environment, shown in the thick line. And this is repeated in every step of the game until the game finishes. And once the agent finishes playing the game, during training, this game is stored in a replay buffer. It is sent to the learner, where this game is used to improve the neural network. And then this neural network is sent back to the actors so that the actors can play better games and therefore enter this self-improvement loop. So it's a natural question whether we could just take the existing AlphaZero agent and just apply it to our tensor decomposition game. But we very quickly found out that this is a very challenging game. So even though in terms of the episode length or the number of steps in the game, it's not really longer than a game of Go, there is a big difference in the size of the board because we have this additional third dimension since we have a 3D tensor. And this also translates into a huge difference in the size of the action space. So whereas in the game of Go, in every state, there are at most 362 possible moves, in the tensor decomposition game, the number of possible moves is just enormous. Because remember, in each step of the game, the player needs to write down these three vectors, u, v, and w, meaning that it needs to choose every single entry in all three vectors. There are also some additional difficulties or specificities of this tensor decomposition game, such as that we have no pre-existing data set of expert demonstrations. We only care about one particular tensor to decompose, and there is no second player to introduce some variability in the games that we play. And also, there are many more symmetries in the problem that can be either a challenge or an opportunity. In Go, you can maybe rotate the board and flip it, but with a tensor, you can, for example, arbitrarily permute its slices and not really change the problem. So we'll see how we can use this later. So as I mentioned before, AlphaTensor is based on AlphaZero, but to solve this challenging game, we had to develop multiple crucial components that form the difference between AlphaZero and AlphaTensor. But it still has the same basic structure. On the top, we have the actors who keep playing this tensor decomposition game, meaning that they start with the matrix multiplication tensor. They use the neural network to build up this search tree of possibilities to decide on the action to commit in the game. And then they keep taking these actions until they reach the zero tensor. Once the game is finished, this game is sent to the bottom part, to the learner, where the learner uses these previously played games and their results to improve the neural network. And then this improved neural network is sent back up to the actors so that they play better games, and therefore we have this self-improvement loop. So now, instead of maybe talking about all the details of the AlphaZero pipeline, I would propose to discuss 6 key ingredients that we used in AlphaTensor that were crucial for obtaining the final performance, but which at the same time, I believe, are fairly general ingredients that can be useful when using machine learning techniques to tackle search problems or mathematical problems.
So just to be sure, the game finishes when you get to zero, right?
Yeah. I mean, there is like a fallback mechanism that in case to prevent infinitely long games, if you take too many steps, we just cut the game short.
And then that episode essentially is considered a failure.
No, it's possible to salvage it because even if you don't reach the zero tensor, you can form like a loose upper bound of how many steps it would take to actually reach the zero tensor, so you can still use that game. But the agent learns quite quickly to finish the games and reach the zero tensor. So this only happens at the beginning anyway. Oh yeah, question?
Yeah, so have you tried other kind of search technique? So from the paper, it looked like there's only you are only using like AlphaZero.
Yeah, so ourselves, we of course did quickly try many techniques when the project started, but our motivation was really goal-oriented. So we just wanted to use whichever technique gets us to new results the fastest. And once it was clear to us that AlphaZero is the fastest way to go for us, we just latched onto it. So we don't have a rigorous comparison of different search techniques. But of course, there have been search techniques attempted in the literature before. And those, obviously haven't reached the same results because AlphaZero improved upon them, at least not previously. So the first ingredient I would like to talk about is the importance of building a good customized architecture for your problem. So first, let me recall what is the role of a neural network in an AlphaZero-based system. It needs to be able to take the current state of the game, in this case represented by a three-dimensional tensor, and the network needs to predict two quantities. One is the policy, so that's a distribution of over the possible next actions to play, ideally giving high probability to good moves. And the second quantity the network needs to predict is the value, which is an estimate of the reward that the agent will obtain if it keeps playing from the current state using the current policy. And the architecture of the neural network that we use is formed by a shared torso, which processes this three-dimensional tensor into an embedding. And then this embedding is passed into these two separate output heads. The policy head, which is a standard autoregressive transformer, and the value head, which is a quantile regression head trained with distributional reinforcement learning. And here I would like to say that maybe in the past I was someone who was usually a bit skeptical about the value of tweaking neural architectures, and therefore I was repeatedly proven wrong and impressed by how many times you're able to obtain clear jumps and improvements in performance just by tweaking the architecture, especially the first part, the shared torso. And so in the final version, the torso operated as follows. First, we take the three-dimensional tensor, and using three different linear layers, we project it down into three different matrices, each time projecting away one of the three modes of the tensor. Now, these three matrices are still 3D tensors because each element in the matrix is an embedding vector representing the column of the original tensor along the mode that was projected away. And then the main chunk of the torso is just a sequence of attention operations that operate over elements of these three matrices. And in each attention operation, we take the elements of the matrices that belong to one tensor slice. So on the slide, I'm showing one example where I'm highlighting in red the elements of the matrices that represent columns that fall into the tensor slice that's furthest away from us. So this would form the elements that are part of one attention operation. And then we would have many such attention operations performed in sequence along different slices and thereby communicate information across the tensor. Now, this way of doing attention is, of course, computationally much cheaper than full self-attention across all the elements in the three matrices. And also empirically, it performs much better, presumably because we have built in some inductive bias about tensor slices into the architecture. Now, this design of the architecture was inspired by equivariance of the problem to reordering slices of the tensor. But we also tried making the architecture fully equivariant, but surprisingly, that did not prove to be beneficial. So in the end, we have an architecture that's only inspired by equivariance, but it's not fully equivariant. The second ingredient I would like to talk about is generating synthetic demonstrations. So in many mathematical problems, especially decomposition problems, we are in a situation like us where we have a complex object like a tensor, and we want to decompose it into a sequence of simpler objects, these rank 1 tensors, but this is a hard problem. In our case, NP hard, in fact. But we can make the observation that going the other way from a factorization to a tensor is very easy. And therefore, we can generate an arbitrarily large data set of synthetic demonstrations by sampling factors at random with completely random elements, and then summing them up to reconstruct the corresponding tensors. And this results in a data set of valid tensor factorization pairs. In this data set, there is no guarantee that the decompositions are actually optimal, and also the tensors in this data set may look very different from the matrix multiplication tensor that we care about. But nevertheless, this step has been absolutely crucial and very helpful to bootstrap the agent's learning at the beginning of training, but also, surprisingly, to achieve the best performance later on.
But it doesn't guarantee that the value will be 0 at the end, or you sample it such that.
No, in this case it does, because what we do is we first sample the factors at random, and then we just compute what tensor do they correspond to. So by construction, those factors decompose the tensor. Yeah. But it's a completely random tensor. Yeah.
But I thought none of the other ones actually use values. And now it sounds as if you're using values.
What do you mean by values?
Like a specific tensor with specific values in it.
Yeah, all of them do.
Okay, all right.
Yeah. Oh, but maybe I'm not understanding the question.
Well, that's fine.
How do you do the synthetic demonstration? Do you kind of pre-train the thing to retrieve this decomposition?
How do we use them?
Yes. Yes.
Yeah. So we co-train on synthetic demonstrations and the games that the agent actually plays. So when I mentioned that the agent keeps playing these games and we write them into a replay buffer, that's one data set of games that is regularly updated and we train on. And then we have this other fixed data set of synthetic demonstrations. And when we train the neural network, we always just sample one game from this synthetic demonstration, one game that the agent previously played. So we train 50-50 on synthetic demonstrations and previous games played by the agent.
So it doesn't matter if the synthetic demonstrations are bad, as you said, they're going to correspond?
That's a stronger statement than what I wanted to make. So the distribution of synthetic demonstrations does matter. So we did tweak, for example, the probability of having a 0 entry in the factor versus a 1 entry in the factor. So it matters what the distribution is. But what I just wanted to say is that it can be sufficient if the synthetic demonstrations are not very similar to the target tensor that you actually care about, or the target object that you care about. But it doesn't mean that any distribution of synthetic demonstrations will be equally useful, or that any of them will be helpful. It might require some tweaking.
So the rule of thumb would be you want them to be different, but you don't want to be too bad.
No, I mean, ideally you would make them as similar as possible to the tensor you actually care about, but that's very difficult to do, or even impossible. Yeah.
So it's almost like having an oracle, but a synthetic, randomly sampled oracle.
Yeah.
So it's like almost combining the imitation learning idea then with the reinforcement learning?
Yeah, for sure. So on the synthetic demonstrations, we just do imitation learning, basically. Yeah.
Okay.
Yeah.
So your policy net, if you go to the previous slide,
Yep.
Like the embedding that you pass to the policy network, is that something separate for each row or column, or is that just one vector for the whole matrix?
So we just take all the embeddings here and we just flatten them together.
Okay, and then like the action space is pretty large, right?
The action space is pretty large, yes.
How does your policy network work exactly? Like, it doesn't have one value per each?
Yeah, that's right. So we use what is called the sampled AlphaZero, meaning that we do not predict a probability for every possible action, but we use an autoregressive transformer for the policy, meaning that it just samples the actions. And that's a hyperparameter, how many actions you want it to sample. We sample 32 actions.
Yeah, you mentioned the episodes that don't finish with 0.
Mm-hmm.
They're still salvageable. Like, do you use like something like hindsight experience replay or something like that, or like a different?
Yeah, that's a great question. Hindsight experience replay would definitely be an option, and we thought it would be pretty cool, but it didn't really show benefit for us. So what we do instead is we just take the episode as it was played, but then we give an additional penalty in the reward for not having finished the episode. And to compute the penalty, we compute this upper bound on how many steps it would still take from the final tensor to zero it out. Yeah. Okay, so the third ingredient I would like to talk about is thinking about how to diversify the target. And I think this is potentially a fairly common phenomenon when tackling mathematical problems, that one is interested in one specific object. In our case, we are only interested in decomposing the one specific matrix multiplication tensor. So in machine learning terminology, we could say that our test set size is only one. And so a priori, if we have this agent that keeps playing the game, always starting from the same tensor, with no randomness and no second player to inject some diversity, we would only have to rely on some explicit randomness to explore and to have diversity in our games. But what we can think about instead is coming up with equivalent representations of our object of interest. And in the case of tensors, there is a very natural way of doing this, because one can take a tensor and change its basis, or in other words, express it in a different coordinate system. This is the same concept as we have for matrices, that you can, a matrix represents a linear operation, and you can express this linear operation in different bases. And all these matrices, or all these tensors, they are equivalent in the sense that they have the same rank, so you can decompose them into the same number of rank 1 tensors. And if you find the decomposition of the tensor in a changed basis, you can straightforwardly convert this decomposition back into the canonical basis, and thereby obtain your matrix multiplication algorithm. And so indeed, this is what we do. At the beginning of each game, before the agent starts playing, we take the matrix multiplication tensor and we sample a random change of basis. So we express it in a different coordinate system. And then we let the agent play the game in this different coordinate system. So this automatically injects diversity into the games played by the agent. And this has the nice feature that it's sufficient for only one of these coordinate systems to be kind of a winning lottery ticket. It might happen through luck or randomness that in some coordinate system, the matrix multiplication tensor is for some reason easier for the neural network to understand or to handle, maybe because it's more similar to the synthetic demonstrations or for some other reason. The fourth ingredient I would like to talk about is handling symmetries. Mathematical problems, they often have loads of symmetries, and this can be either a challenge or an opportunity or both, depending on where these symmetries arise. I already mentioned the input symmetry, so symmetries of the tensor or the state of the game, where you can express this tensor in a different coordinate system, change its basis, and this is an equivalent tensor. And we have used this symmetry to diversify the target or diversify the games we play. We have also used a cheaper to compute change of basis as data augmentation. So whenever we present a tensor to the neural network, either at training or acting time, we randomly permute the slices in the tensor. And also we indirectly use this input symmetry to design the architecture. One type of symmetry that is often important to handle is symmetry on the output size, especially when it's possible for multiple different actions to result in exactly the same next state. And this can indeed happen in our case, because remember the action is these three vectors u, v, w, which implicitly describe through their outer product the rank 1 tensor that we are going to subtract from the state of the game. And therefore, it might happen, or it is the case that if you were to multiply two of these vectors, let's say v and w by -1, you do not change the outer product because the two -1s cancel. So there are at least 8 different actions that lead to exactly the same state. And this can cause trouble to the agent. But we can sidestep this issue, in particular by canonicalization. So in our case, we insisted that the actions are always presented in a canonical form, where the first non-zero entry of u and the first non-zero entry of v is always strictly positive. Another symmetry which often arises in decomposition style problems, and certainly in ours, is symmetry on the level of a sequence of actions. So because addition is of course commutative, and we are interested in decomposing our tensor into a sum of rank 1 terms, it does not matter in what order we write down these factors. And initially, we were quite worried that the agent might be quite confused. There are these n factorial ways of writing down the same factorization. But it turns out that the agent very quickly discovers or finds a preferred ordering and always outputs the factorizations in roughly the same order. But nevertheless, we found it useful to leverage this symmetry for data augmentation. So whenever the agent finished playing a game, meaning it finished writing down a sequence of factors, not only did we take this one game and wrote it into the replay buffer, we also made a copy of this game and slightly permuted the ordering of the factors in the game, and then also wrote this copied, slightly modified game into the replay buffer. And this also brought an important benefit. The fifth general ingredient I would like to talk about, which applies to, I would say, maybe all mathematical problems, is that in these settings, we actually care about the maximum reward rather than the average reward, which is the standard setting in reinforcement learning. What I mean by this is that when we have an episode that achieves really high reward, that is what corresponds to discovering a new algorithm or a new mathematical result. In our case, a new algorithm for matrix multiplication. And we don't really care if at the same time the agent has played loads of games with really bad reward. So we don't care about average reward. We only care about the max reward. And one way in which one can exploit this is to use risk-seeking value predictions. So if you remember, I mentioned before that our value head in the neural network, it's trained with distributional reinforcement learning. And what this means is that when we query the value head and give me the value of the current state, it does not just predict a point estimate. It predicts a whole distribution. And so we can form an optimistic estimate based on this distribution. In our case, we average the top 25% quantiles to obtain this risk-seeking prediction, which encourages the agent to try actions that on average may not work out very well, but sometimes may really discover an improved algorithm. The second feature of mathematical games like this one is that the environment is deterministic and there is no second player. These are single-player games. And so what we can rely on is the fact that when we have an episode that achieves high reward, this high reward is real. It's not an artifact of randomness or luck. And so if we have such a good game, it's a truly good game, and it might be worth overtraining the network on it more often. And this is indeed what we do. We have a separate replay buffer for the highest reward games, and we train on this for 5% of the time.
I'm sorry.
Yep.
I'm actually a bit confused here. So the quality of the game is the length of the sequence to get to zero.
Yeah.
Right? So in AlphaGo, it doesn't matter the sequence. The point is actually to go to 0, 1, so win or lose.
Yeah.
So here it seems to be more difficult in a certain sense to me. Like in a certain sense, because there will be a huge amount of trajectories that are leading to the same value. So how do you distinguish those values? Which one is good or bad?
As long as the trajectory has the same length, they are equally good. The unification between the two settings is through reward. So in our case, we give a reward of -1 for every step. And in the case of a game of Go, you don't give a reward. You give a reward of 0 for any step, except when the game ends. You give a reward of 1 or -1. And in both cases, we just optimize for the sum of rewards.
Yes, we can take it offline. But my point is, so there will be so many equivalent trajectories of the same length.
Mm-hmm.
Until there is one that has one step. The sequence is one step less.
Yeah.
I have a hard time to see how to distinguish, but probably not all of them are, in a certain sense, equivalent to get to the one that is one step shorter, right? In a certain sense. And I don't see how you are actually able to distinguish those.
I'm not sure, is this a question about how the neural network is able to do it, or whether there is an explicit mechanism?
I don't know myself, so we can take it offline. It's just more like a brainstorming for me. Sorry.
I would just say the general high-level answer that through generalization, the network learns about what kind of pattern might be amenable to future improvement, and then hopefully plays those patterns more often. But yeah.
Yeah, so you talk about this basket buffer, right? So how is it different from prioritized replay? I mean, you can also achieve that with prioritized replay as well.
Yeah, that's just a question of implementation. Like if you had a prioritized replay, which puts a weight of 5% on the best games, it's the same thing.
So when you say optimize for max performance, I mean, this is what games typically do, right? So you don't optimize expected performance, even in game like Go and chess, right?
I mean,
so what is there something really novel here compared to what was done before? So you just want to say that this is important and it's different from reinforcement learning applied to Markov decision processes.
Yeah, so there are a few things. So yes, first of all, that's definitely true. It's different from just the usual setting of RL applied to Markov decision processes. But I would say also in the case of Go, we do optimize for average reward in the sense that we want to maximize the probability of winning games overall. It's not like what we care about is to play this one most amazing game of Go. We want to have an agent that is going to win games of Go on average as often as possible.
So you would actually, so if you look at these games, I mean, you are trying to anticipate what the opponent is going to do.
Yeah.
So you take the best, you do an expectation on everything, even if the player is doing something bad, the opponent is doing something bad.
I believe so, yeah.
Because normally you assume best response of the opponent, right? So
yes, I mean, you can take this offline, but I think it's different because you still want to optimize the probability of winning the game, and you're not optimizing for discovering one amazing Go game where you, like, I know what would be a metric of an amazing Go game, but maybe the most impressive Go game. Whereas here, we don't care if the agent plays loads of games in which it completely fails, which, let's say, in the case of Go would be really embarrassing if the agent played a lot of really bad games.
Okay, that distinction is interesting.
Yeah. So the final ingredient I would like to talk about was really crucial in the final push to obtain our best results, and it was particularly exciting to see it in action. This ingredient is training a generalist agent, meaning that we trained a single agent with a single neural network to decompose matrix multiplication tensors corresponding to all these base matrix sizes, 2 by 2, 3 by 3, 4 by 4, and so on, instead of training a separate agent for each matrix size separately. Now, first of all, this is, of course, computationally much more efficient to only train a single agent. But two, it just performed much better. And we were, in fact, able to analyze the transfer that the agent discovered between different base matrix sizes. And we were able to confirm that the agent found some way of transferring knowledge even between those base matrix sizes where there is no mathematical relationship known that would explicitly facilitate such transfer. So it must have found some patterns that are not known to us to transfer between the different targets. So zooming out, I presented AlphaTensor, which is based on AlphaZero, and I showed you the 6 key ingredients that form the difference between the two, and which I believe are fairly general when one seeks to apply machine learning techniques to search problems or mathematical problems. And out of these 6, I would say 4 were absolutely crucial for us, meaning the system would perform much worse without any of them. This is having a bespoke architecture, generating synthetic demonstrations, diversifying the target, and training a generalist agent. The other 2, leveraging symmetries and optimizing for max performance, they also brought important but smaller gains. Zooming out more, in this talk, I showed you how discovering algorithms for matrix multiplication corresponds to the problem of tensor decomposition, and I showed how this problem of tensor decomposition can be framed as a single-player game. And then I talked about the AlphaTensor agent, a reinforcement learning agent that can learn to play this game, and in fact can learn to play it relatively well in the sense that it discovers quite complex algorithms like this one, which can surpass the state-of-the-art on multiple base matrix sizes. And now I would also like to take a little bit of time to discuss what I believe are the main limitations of the current version of AlphaTensor. So first of all, we had to choose a finite entry set for the elements in the vectors u, v, w that the agent needs to or can pick in every step. This is not a problem when we apply AlphaTensor in a finite field, in which case we can use all the field elements. But if we say, let's say, seek algorithms with integer coefficients, we need to restrict to some finite set. In this case, we used -2 to 2. This might, of course, mean potentially missing out on algorithms that use a different entry set. And second, this might be obvious, but still important, this being a reinforcement learning agent, and in the current setup, there is no promise of optimality. So even though the agent has matched or exceeded the previous state of the art, even faster algorithms may well still exist. I would also like to comment on the generality of this approach on 3 different levels. So on the level of problems, as AlphaTensor is described, it immediately applies not only to matrix multiplication, but to any bilinear operation, unchanged. And we have a few examples of this in the paper. We have a specific type of matrix vector product and also an example of rediscovering the Fourier basis. But more generally, an approach like AlphaTensor, I believe, can be extended to other decomposition problems. We again have an example of this using the notion of border rank in the paper, where we can discover approximate matrix multiplication algorithms. And I also believe that multiple of the ingredients presented here can also be useful when tackling other search problems using ML techniques. On the level of spaces that AlphaTensor can operate in, I already mentioned it is easily adaptable to discovering algorithms in finite fields. It would also be easy to adapt it to complex numbers, or in general to any ring where a multiplication table can be provided. And finally, on the level of objective functions, so what we optimize for. This being a reinforcement learning agent, the reward can be really anything. It doesn't have to be differentiable. So we have seen the basic example of optimizing for rank or theoretical time complexity. I mentioned we can optimize for actual practical runtime or latency, but we could optimize for anything else. So maybe memory usage or energy usage or whatever property of the algorithm we would like. And finally, I would like to leave you with maybe a message of inspiration. In this work, we have seen this path of AlphaZero going from playing human games like Go, chess, and shogi to playing this abstract tensor decomposition game with potential of real-world impact. And if you like this line of thinking, I would invite you to maybe think of your favorite problems and see if they might benefit from any of the ingredients I presented here. And with that, I would like to open for any comments or questions.